Okay, can I get everyone's favorite color? John, do you want to start?
Green.
Green. Baird?
Yellow.
Is that how you start all the meetings now?
Jared, you said yellow?
Yellow.
Oh god. Yeah, Andre.
Gabe, are you taking our data right now?
Yeah, mining.
Are you going to sell this information to somebody?
Everybody just choose the same color, so his example
Data
here is
is
useless.
All of them are
Don't worry.
green though.
Whoever says they don't like purple, they don't like this club.
Andre, what did you say? You
I
said
said blue. I said blue.
you're blue. Who else we got? Yash, what's your favorite color?
Red.
Yash is red. It's two.
Red is the fastest color.
Red, that's true. Courtney?
Purple.
Oh,
Nice.
it's galaxy colored.
I like it.
Yeah,
Zulu?
but it's mostly purple. Very appropriate.
It's galaxy colored.
Sure, blue.
It was blue. Elena?
Can I say black?
Yeah.
Okay, cool.
Black. Raphael?
Are we choosing favorite colors?
Yeah.
Blue then.
Blue. That's 3. And who else did I miss?
I love how my color is just singled out.
Yeah.
It's great.
Who's dot dot? I never know who dot dot is.
Lu?
There's some. Who's dot dot? Can you guys tell me? Do you see dot dot?
That's what? That's just more people.
No, there's someone.
No, there's an
who's
actual
dot, dot.
dude who's like dot dot.
What?
Who are you?
Who's
dot
dot?
dot?
I can't see dot.
Identify yourself in the chat. We got a second black though.
I'm not seeing dot dot.
Skype's bugged.
That's Sevak.
Okay, I'm also blue.
Oh, Sevak, you're Sevak on my screen.
Sevak. Cool. Alright. So what does it kind of look like?
Faraz is here. That's the
Blue. Red. Purple. Yellow. Faraz, what's your favorite color? Green. Black. You guys' favorite color squad? 2, 1. We're pretty spread out on this one. There's a few blue fans, but it's pretty good. All right, now to the lesson. I will sell this data later.
Okay. That's the lesson. Okay,
Yeah.
thanks.
Yo,
Yeah.
hello?
Hey,
Oh, wow. Okay, I plugged in my mic for the first time. Hi, everybody.
Cool.
I'm Savic.
your mic sounds amazing, by the way.
Oh, yeah, it's
Hi,
RTX
friend.
Boys. Oh, hi.
Cool.
All right, sorry. Continue with your lesson.
Yeah. So, quick review. What did we do last week? I honestly don't remember. Can you guys remind me?
We talked about our favorite fruit.
Okay, last week we did fruit. What else did we do? Was that it? Did we end off there last week?
Sir Mister.
Mister, nice. I like that. Mister, so kind of like a real application of ADC, especially an ADC that's external to the microcontroller. Why you would do that, and different ways you can accomplish it. I think that was the gist of it. I don't remember anything else specific. But cool. So this week we're going to talk about digital to analog. So it's literally the opposite. So if you see analog to digital here, and converter stays the same, you just kind of swap them around. So it's going to be digital to analog converter. And with both of these, sometimes people call them different things. So sometimes you'll see something like D to A or B/A or even D to A. Some people do the same with the other way around, analog to digital, A to D. Like you'll hear this especially from sort of older engineers. This is very common. So just convention in case you come across it. A to D. And you said this is all digital to analog converter, right? You can imagine digital to, I guess this would not be capital. You can imagine that the same way we like to convert analog to digital, sometimes we want to do the opposite. This is especially popular in audio applications where you want to either process audio or send audio out to a speaker. And we actually also use a digital to analog converter inside our car, which we'll talk about in a second. Here. Let's skip this for now. So you have the same sort of ideas, right? We remember for an analog to digital converter, we had a certain number of bits, right? Maybe 10 bits or 12 bits to play with, and then we call that our resolution. Right? We also had a reference voltage. And you have all these same kind of things for the DAC as well, the digital to analog converter. Whereas before for the ADC, the analog voltage reference, or the reference voltage, sometimes we call it VREF, was the maximum voltage that we could sample on the analog side, right? So if you had our ADC, and this was some analog thing we're sampling, comes in, and out we send digital. You had a maximum sort of voltage that you could sample to, right? That the ADC could accept any voltage within this range. That was the reference voltage, VREF. And for a D to A, digital to analog, you have the same idea, right? This completely flipped. So from our microcontroller, we're going to send it some digital. And we're going to hope we can get a good analog signal out. And the analog signal will range from anywhere from 0 to VREF. Right, and this is something that you get to specify. Usually there'll be a little pin on your DAC, so if it's external to the microcontroller, it's just going to be an IC with its own pins, right? Little chip, and one of those pins will be the VREF pin, and on there you can put your own voltage. If you have a readily available voltage, like 5 volts or 3.3, that's something you can put there. You could also use that voltage reference IC that we talked about before as well, that generates exactly the reference you want. Whether that be 1 volt, 2 volts, 2.5 volts, 3 volts, you get to pick that. So it's entirely up to you and your system what you decide as your VREF. It could be anything really. And like with the ADC, we had the bits, right? So we had the resolution here as 10 bits. What that meant is that we had 2 to the 10 different levels, right? 2 to the 10 levels that we could split up our analog into. So the way the ADC worked is that it sampled an analog voltage, right? And split it up into these little chunks that we called the different levels. So it would kind of look like this inside the ADC. Maybe I'll just draw it on top. Right, kind of look like this little kind of step guy. And the more levels you have, or the higher resolution you have, or the more number of bits you have, then the smoother and smoother and smoother your signal gets, right? If I only had 2 to the 1 levels, I only had 2 different levels that could be, then my signal would not look very good, right? It would only look something like low, high, low, high, low, and that'd be a very terrible approximation. Concept is very similar with the digital to analog converter. We have 10 bits for resolution. We have 2 to the 10 different levels that we can play with. And so digital to analog is almost a misnomer because you can never really create that analog again. Once you're digital, you can only recreate an approximation, right? And that approximation is this sort of digitized analog voltage. So you'd want it to look like a super smooth thing, but in reality, it'll only look as smooth as the number of bits you have. So it would only look like this. You can never get exactly your analog signal back, right? But you can get close. You can imagine if my VREF is 5 volts, right? I can go anywhere from 0 to 5. And I have 2 to the 10 levels. So 2 to the 10 is 1024. Someone correct me if this is wrong. I know I always get these wrong. But that means I have 1024 different little levels between 5 volts that I can play with, right? That means that each level would be approximately 5 volts divided by 1024. What would that be in math? Grab the calculator. 5 divided by 1024. So this looks something like 0.00488 volts per level. So what that means is that our digital to analog converter can get that close, right? Where the difference between each step is 0.00448. Right? 0.00448. And again, if I have more bits, right? If this were 20 bits, I'd have 2 to the 20 levels. And that's math I can't do, that's something, right? But then this number, so it'd be huge. It'd be so much bigger. And you can imagine if I have the same voltage reference, but I'm dividing by a much bigger number in the denominator, I'm going to get a much tinier volts per level. So my analog signal would look a lot closer to analog than this one would. It'd be maybe kind of like this, right? So all you can ever do is approximate, and usually we get pretty good with the number of bits. And even this is really good. Especially in our application, there's no real scenario where we need to be that precise, where we're like at about 5 millivolts. So digital to analog converter is a really nice and useful, quick way to create a pseudo analog. It's not exactly, but it's really, really, really close. So sometimes this exists inside the microcontroller, like we always draw. So if I have my microcontroller, so microcontroller, or sometimes MCU, right? These are the same thing. People write them in different ways. And it has pins on the outside, right? That's how it interfaces with the outside world. So sometimes, if I'm lucky, my microcontroller has a DAC inside it. Right? And the little piece of silicon inside, it has a digital to analog converter. Just like we saw before with the ADC. The difference is that it's not as common. It's almost impossible to find a microcontroller without an ADC these days internally, right? ADC is almost second nature to every microcontroller, right? This is almost guaranteed. And if you find one without, then it's probably better that you find one with an ADC internally, because they're so cheap now. But the digital to analog converter is not as common, right? And it turns out that in the microcontroller Team Phantom's using, it doesn't exist inside. We don't have one of these, unfortunately. So that's for the Team S570, right? Sad news. Another very popular microcontroller is an STM32. This is super popular in the automotive industry. So people love this chip because it's cheap and powerful and has a lot of different little peripherals inside. So it's called the STM32. This one does have a DAC inside. That's nice because that means that straight from the microcontroller, I'm going to have a VREF pin, right? And I'm going to have a pin that spits out my analog signal. Remember, kind of pseudo-analog, but as good as we could get. The TMS570 has no way to do this. There's no DAC inside, so it can't spit out any analog. So they call analog A, I guess. There's no analog coming out of here. Right, so what we have to do is use an external chip, right? Similar to how we did an external ADC. You would just do an external DAC chip. Right, so we're going to talk to it with digital, and in later lessons we'll talk about exactly how you would do that. But we talk over digital. And then we get to send our analog out. And then we're happy, right? And you're going to have to provide a VREF pin here, a ground pin, a power pin, and a few other things. So on the VCU, let's take a look. Any questions so far?
Why did you choose a pin without a DAC?
A microcontroller, you mean?
Oh, sorry, yeah, microcontroller.
Yeah, it wasn't at the top of our minds, to be honest. And yeah, so probably we could have chosen one with the DAC inside, but there are a number of advantages for the TMS570 compared to the STM32.
Mm-hmm.
The first being that the TMS570 comes with an automotive rating. So usually what that means is that you'll see the chip with a Q at the end. So there's going to be some other numbers here, but Q1 usually. And usually that's a dead giveaway that it's automotive rated. And what that means is that usually it's the same chip inside, but what that tells you is that the manufacturer of this chip, so TI in this case, spent more money and more time to test it. So what this means is that they did accelerated life cycle tests to make sure that the chip would survive in an automotive environment, and also extended temperature checks and tests as well. So usually having this designation is going to make the chip cost more, but you get that rating that tells you that the chip can handle automotive temperatures and should be life cycle tested to last as well.
Mm. Wait,
So that's number one.
As the other one is also automotive rated? Like it's popular to the other cars or whatever?
Yeah, it is. I'm not sure if they automatically come with a Q1 rating though.
Oh, okay, gotcha.
Yeah, and there may be some variants of it that do, but I'm not sure if they all do. So that's one reason. The second reason is that very commonly STM32s are Cortex M4. So that just means the processor architecture inside. This one is R4, so it's rated for safety critical applications. And specifically what that means for ours is that, inside the microcontroller, right? The chip. Remember we talked about all those little peripherals you had, those little building blocks inside the chip, right? So we had an ADC, for example. You're going to have a little GPIO chip, which you talked about before. And these are all just little building blocks in silicon. You don't actually see these. It's all inside the chip. You have memory, right? And like RAM, flash. All this is inside the chip, which is great. A bunch of other things we'll talk about later, but then the processor, the CPU. And in the TMS570, what's cool is that, right here, the CPU box actually has two little CPUs running together. You can kind of think of it as dual core, but each of them actually run the same commands. Whereas in dual core, each one would kind of run its own stuff, right? And you sort of get that parallel output. Each CPU core in here, they process the exact same instructions. This one actually delayed by 2 clock cycles, and actually flipped physically. But the idea is that if one dies, the other one's fine to take over, right? So you have that redundancy in case one of your processors completely craps out. And so that's a big plus in terms of reliability, which is another reason we went with this one over the STM32, right? So this is something that you can't really add externally to your microcontroller, whereas a digital to analog converter, we can just buy a $3 chip, right, and put it outside. So that was the reasoning. Both are great chips. There's a reason this is so popular as well, right? So, but that was the reasoning. Okay. Cool. Good question. So, as you know, there's our chip, TMS570, and there's the other numbers. And if you squint really hard, you'll see that Q1 there at the end. So that's what tells you it's automotive rated and has gone through those life cycle tests and temperature tests. So, voila. There's the digital to analog converter. So just like you'd imagine, it's an external little chip that the TMS570 is talking to, right? So it's, you can see these traces kind of coming out. And then they go to the chip, right? And so what goes through is this digital communication protocol that we're going to talk about in a different lesson. This chip also gets 5 volts of power, ground, and then VREF is connected straight to 5 volts for us. So it kind of looks like this. And the output of the DAC is the analog signal that goes to this little test point. And it's a little hook that we can hook a little oscilloscope probe to and measure the signal. It also goes out to the connectors so that it can go to the rest of the car. So DAC. Number of pins, right? A bunch of them are the digital stuff that the microcontroller is sending, right? Digital. We said we have one pin that provides power. One pin that is a VREF that we connect to 5 volts as well. They're connected. One pin that's ground. And then an analog pin that comes up. And depending on the model you use, some actually have 2 analog pins, which is cool. So with the same number of digital pins, you can actually get 2 separate, individual and independent analog signals coming out, which is really useful because you basically have 2 DACs in one at that point. And the resolution, 8 bits. So why do we have this? Well, the idea is for the foot pedal. So what happens in our car, and per the SAE rules, you need to do this. So if this is the foot pedal, I feel like I've drawn this before. Right, this is the foot. This is the pedal. What we need to do is basically measure this angle, right? The more our driver stomps his foot down, the more acute this angle will get, right? So if the angle is smaller, then we're assuming the driver is requesting more torque, right? Driver wants more torque, right? More torque just means that the motor is using more power to spin whatever load is attached to it. In this case, the rest of the car, the chassis, the driver, the wheels, the seat, right? So, and there's actually two different modes you could do. You could interpret this as if the angle is smaller, the driver wants more torque, or you could interpret this as the driver wants more speed. Very big difference. You can imagine that if the foot pedal directly controls the speed, that means that, let's say if I'm not pressing the foot pedal, right? If I'm not pressing the foot pedal, I'm saying, okay, I want the motor to be at 0 speed, car to be at 0 meters per second, for example. Let's use real units. 0 kilometers per hour. If I'm stepping on it and the foot pedal is maybe here, right? Angle is smaller. And let's say here I'm saying, now I'm assuming that the driver is requesting 60 kilometers an hour. That means that for you to maintain 60 kilometers an hour, you're going to have to keep your foot pressed halfway forever. And whenever you lift your foot off and the pedal springs back to its normal position, your car's going to immediately stop and go to 0 kilometers an hour because you've mapped your foot pedal to the speed of the motor and the speed of the car. So this is annoying because you can imagine every time you lift your foot off the accelerator pedal, you wouldn't want your car to come to a dead halt at 0 kilometers an hour, right? This makes sense if you're stopped and you haven't started yet. But when you're already moving and you let your foot off the pedal, you don't want it to spring back and automatically map this initial foot pedal position to 0 kilometers an hour, right? So that's why people came up with mapping the foot pedal to torque, right? And it turns out that torque from the motor is proportional to acceleration of the car. So essentially what you're doing is mapping the foot pedal to acceleration and not speed, right? And that's a lot more conducive to what we understand when we drive our cars normally today, right? When you stomp on your foot pedal, you can feel the car accelerating. And if you keep it at a certain position, it'll keep accelerating. And if you let go of the foot pedal, the car is not going to automatically jump down to 0 kilometers an hour. It's going to drop to 0 acceleration, right? And you're just going to coast. So that's what kind of they call coasting, because you're no longer actively accelerating the car. Right, so that's why we use torque control when we map the foot pedal to the motor, because we want to be able to accelerate with it and not have the car immediately stop whenever we take our foot off the pedal. So per the rules, I got sidetracked a little bit. Per the rules for your foot pedal, like I said, you need to measure that angle, right? In the FSA rules, and actually in most cars as well, you're going to have two sensors here. They really want that redundancy. And that's because this is the thing that controls if your car goes, right? This is a weapon of mass destruction. If you're in front of a wall and one of your sensors fails and accidentally thinks that you're flooring it, your car is going to ram itself into the wall, right? So we have to be very careful with these signals, and FSA refers to them as safety critical signals because of how important they are and how dangerous they could be if we don't take care of them properly, right? And the automotive
I just want to
industry,
add
of
on
course,
to.
please, yeah.
Sorry, one thing is that if that ever happens, you can always, well, ideally you could just slam on the brakes and the car will shut down.
Wow, what mechanism would that be?
Bonus points for whoever can figure that out.
Anyone know? This is specific to Formula SAE. I'm not sure. This is not like a generic thing, but you want to take it away for us?
Yeah, it's the BSPD board. Basically, if if it senses any current draw from the motor and there's hard braking, then it'll send a signal to the shutdown circuit to shut down the attractive system.
Cool. So this is something that for us is designed for us, which is really good, and that is required by the rules as well. And it gives you sort of like a fail-safe. If things are going wrong, the driver can emulate this command, and the car should shut down, which is to stomp on the brake while this event is happening. Like if it's pulling a lot of current because it either broke or you're doing it on purpose. We have that. Yeah, Mahmood.
Yeah, does that not mess with driving with 2 feet, like 1 foot on the brake, 1 foot on the gas?
Yeah.
Really good question, actually.
Yeah.
Or is it like you have to be
careful.
like really into it?
If you stomp on both, then it'll trigger.
So not like if you're just feathering the gas, right?
No.
Okay, thanks.
There's a defined limit, right? And that's 5,000 watts of power being drawn from the battery. So as long as you're under that, and under the definition of hard braking, which is very vague in the rules, then it's not going to trigger. So we kind of get to set that. And so we could set hard braking to like fully stomping on the brake, 80%, 70%. I don't remember what we have right now for us.
I think it's still undetermined.
Yeah, it's something that we're gonna tune while testing, right? To see like, oh, it accidentally triggered while
Yeah.
driving. Maybe we should kind of test it. So
Yeah, another thing we need to sorry to cut you off there, is
please.
the
Yeah,
brake sensor. We've been on and off that for a while now. That's one thing we need to go after, because then if we figure that out, it'll make it easier for us to figure out how hard we need.
Yeah, for sure.
I have a question about the signals.
Please.
So, are these just gonna be like 8 wires with an analog signal going through it to the microcontroller?
Sorry, why 8? Did you say 8?
No, I said, are these gonna be wires with an analog signal just going straight to the microcontroller?
Yeah, basically that's it.
But if there's safety critical signals, shouldn't we have like something safer than that? Just
Yeah,
for noise.
we could. The plan right now is just to shield it and pray. So wrap them in shielded wire. And we're gonna test it, right? We're gonna make sure that it survives that long wire, especially because it's not necessarily passing by the motor per se. The same way, like in the thermistor board we talked about the other day. This is the motor between the wires are literally going right across it. Let me just draw this better. So wheel, left, right, front of the car, back of the car, right, wheel, wheel. So we had battery box left, battery box right, and motor, right? Oh god. And then we had wires going here. And this was the son of a bitch noise generating monster, right? The VCU is here, kind of, somewhere here, right behind the seat. And the foot pedal's here. So we're hoping that this amount of noise, or this distance traveled, isn't as noisy as this kind of area. Especially if we shield it, because there's no huge generator of noise, like a big motor around here.
Mm-hmm. Yeah, that's a good point.
So that's the hope for now, right? And that's why we think that it's okay to just shield it. But that's definitely something we want to test. Absolute worst case, if we notice that these signals start going nuts. Sorry, I'll just leave this actually. If we notice that these signals start going nuts and the car is freaking out and accelerating when it's not supposed to because those analog signals are picking up noise, driver's going to have to stomp on the brake, shut down the car, and then we're going to need to design something better than this.
Mhm.
Right? We'll need to probably put a little ADC here. Take those analog signals and then send their digital,
Mhm. Okay.
which we know how to do by this point, right? So that should not be a huge deal.
Yeah.
But yeah, no, that's a great point. Thanks for bringing that up. So C2 critical signals, we have two, right? We want to make sure that we have two things measuring the foot pedal, and we don't want to only trust one at a time. And so in the rules, there's a number of things we need to check for. And some of this can be done by the inverter, but not all of it, specifically the 10% rule, which I'll mention. And so what you'll see often is in DIY conversions, where they kind of just buy a kit for like an electric vehicle and convert it, usually from a gas car to an electric car. What you'll see often is so like an inverter. And turns out that the inverter and motor we have are part of a DIY kit, which is part of the reason how we got them donated to us. But like often what you'll see is just the foot pedals plugged straight into the inverter, right? And the inverter will do a couple checks, but not all of them, right? And so the rules are a little more stringent than just what the inverter can do. And so what we do is we basically intercept it, right? So where's the VCU? Okay, VCU is too far. We've got to move on without it. We take these two signals, send them to the VCU, do our checks, and then send it back to the inverter, right? And all the inverter cares about is one analog signal. It's not looking for the two that we have as redundancy. I think you can reprogram it to take two, but to reprogram it, you have to send it to the manufacturer. They reprogram the inverter for you, then they ship it back. And we've already done that once. Not to mention it doesn't measure everything we need to. So that wouldn't help us a lot. But the VCU takes these two signals, does all the checks we need, and then recreates one analog signal to the inverter. And so essentially what we're doing is we're pretending to be a foot pedal at this point, right? The VCU is now pretending to be a foot pedal that the inverter just sees as stomping on. And the way our inverter reads this is with a 0 to 5 analog signal, right? So it's called the Curtis 1239E inverter. And its input is a 0 to 5 volt analog signal. Right, so that's what it uses to determine how much torque it should send to the motor, or how much torque the motor should exert on the system, pardon me. Right, so that's how it decides basically the motor controls. So the checks that the VCU does, mandated by the rules, are as follows. So very clear, the 2 straight lines and 1 squiggly line, right? That totally means something. So let's roll with it. First thing is short checks. So like we've said before, all a short is just connecting 2 points, right? And the most dangerous short is connecting power to ground, right? Because there's no resistance in a short from power to ground, you get infinite current, and that usually damages all of your equipment. Right, so that's the most dangerous short. In this case, we're checking for signal shorts. So I have 2 analog signals, right? Analog signal 1, analog signal 2. And I said that, actually I didn't say it, but there's some voltage, right, between turns out that they're actually, the two sensors we have different voltage ranges. So one is 0 to 3.3, and one is 0 to 5. So what a signal short check is, I'm pretty sure I just made that up. But what this check does is that it makes sure that this signal is not shorted to ground, 0 volts, also known as ground. Right? And it also checks to make sure that the signal is not shorted to power. So in this one, it'd be 3v3. And this one would be 0 volts and 5 volts. The problem is that we're in a car, right? Things are vibrating around, rattling around. It's very possible that a connector could unplug and that this signal wire accidentally touches the 3.3 volt signal, 3.3 volt power wire that's in the same shielded group of cabling, right? So if these two conductors touch on the ends where they're exposed, your microcontroller or your inverter may be interpreting that as, hey, I stomped on the pedal. It's at full throttle, max voltage. Let's go, right? And that may not be the case. Again, you may be in front of a wall, but your signal's rattled out and they shorted together. And so accidentally your signal is now reading 3.3 volts. Let's say the same thing's happening here. It accidentally started reading 5 volts. You really don't want this to happen. You can imagine that it sounds like a bad time, right? So what we actually do is, interestingly enough, this is actually like an interview question I had once. The question is, how do we sort of prevent this from happening? Or how do we distinguish between knowing if I've stomped on the pedal and I'm actually requesting full torque, or if my signal has shorted to VCC? If we just imagine there's just one signal for now. Someone want to hazard a guess? Is the question clear? Basically, how do we tell the difference between, if we're a microcontroller or we're an inverter and we're reading 3.3 volts, how do we tell the difference between if the driver was actually stomping on the foot pedal or if it accidentally shorted to power? What would we do?
Sample it, like, over time.
Okay, over how long?
I don't know.
Remember, this is happening really quickly, right? Like, the microcontroller is sampling it, in our case, every millisecond. So 1,000 times a second, we're reading this foot pedal and we're updating what we should send to the inverter, right? The VCU is reading this signal 1,000 times a second and then updating what it should send to the inverter at that rate as well.
But if you're sampling that 1,000 times a second, you'd probably read the could read the angle of that foot pedal. Like, it'll be gradually go up. It won't instantly just shoot up. If it instantly shoots up, that's a short. If it's more gradual, then we want full torque.
Okay, so you're saying, like, if my foot pedal's here and then I see this, then it's a short, right?
Yes.
So you're putting a limit on the rate here at which it rises, right?
What if I actually meant to stomp it really fast?
Yeah, what if Faraz actually stomped it though, and he wants to accelerate out of a corner? The stomp rate.
Stomp. Would it be just one vertical, like, just a shoot up? Because if you actually stomp it that fast and our sampling rate's that quick, it'll be more like a diagonal, wouldn't it?
Yeah, it depends how fast you can do it. There may be possible. You may be
I've
able
got
to
a pretty
tell.
good ankle, Andre.
He's strong. His calves are made of steel. Yeah,
I
but
think
yeah,
it's pretty good actually.
it's not terrible to be honest. I think this could be done.
Yeah.
It would take a little bit of processing because you're going to want to filter this, and then you're going to need to have measured the rate at which it goes up. So you maybe here you can tell if it was a short or not. But I would be down for that. So what if, and then same thing on ground, right? So now the question is, if I were up here already, kind of feathering the pedal, and my jump is much shorter, it's going to be a lot harder to tell the difference, right?
True. Makes sense.
Same thing as if I were feathering it down below and I showed it to ground. This is a lot safer because the car would just stop, right? But you don't really understand why it stops and all that stuff. This is definitely the most dangerous case. Yeah, this could theoretically be done. I haven't seen it be done, and I think there are some dangers not knowing how to differentiate all the time. But it could theoretically work. What we actually do is we limit the allowable voltage range, right? So if this is the pedal unpressed and this is the pedal pressed, what we say is that the way we actually mechanically set up the sensor is that when it's not pressed at all, spit out something like 0.5 volts. That's the 0% throttle position. When you're fully pressed, send, so let's say, I guess from the 3.31, right? So let's say send 3 volts. Never send 0 or 3.3. Never send 0 or full power. Those states are not allowed, not defined, and not what you should expect to see. So at 0% throttle, we should be reading 0.5 volts. At 100% throttle, we should be reading 3 volts, for example. And if you're on the 5 volt sensor, maybe 4.5 volts. That way you know instantly, if you're ever measuring 0, if I'm ever measuring 0 volts, if I'm ever measuring 3.3 volts, I know it's a short. No matter what. I don't have to differentiate between, did he mean to stomp? Did he not mean to stomp? Was it an accident? I know right away this is a short because this is not a defined voltage from 0% to 100%. And so we do this with both sensors. We have an allowable and expectable range of voltages that we should see on the throttle. And if we ever see 0 volts, if we ever see 5 volts, or 0 volts or 3.3 volts in the other sensor's case, then we know it's a problem. We know immediately, if we see that, stop sending voltage to the inverter. Automatically send 0 volts and make sure that it stops. Does that make sense? Andre?
Oh, yeah.
Cool. So those are some of the biggest ones. So we do that short check for both signals, both safety critical signals. The other one defined by the rules is that you want to make sure that your signals are, remember we have two signals on the foot pedal. We want to make sure that they're within 10% of each other. This is basically a redundancy clause. Make sure that they're measuring the same thing reasonably closely. They can differ up to 10, 5%, 6%, 9%. But if you see one kind of drifting off, you start to assume that maybe the sensor got disconnected. It's not coupled to the rotation shaft of the foot pedal anymore, and you should stop the car as well. So that's what the VCU checks for, right? Checks for this, checks for the shorts. And if both those things are good, I guess all three, right? Or however many you want to consider. The ground short and the power short on signal 1, the ground short and the power short on signal 2, and the 10% within each other. Then the VCU says, okay, I've signed off. I'm good to go. Let's send this out to the inverter for an actual torque request to the motor. So that's basically why we don't connect the throttle, the foot pedal throttle straight to the inverter. That's why we pass it through the VCU to do these checks, make sure we're safe. And that's also why we have a digital to analog converter, right? We can't send this analog normally. So we need that external digital to analog converter to allow us to even have this torque path, right? So this little chip here is what makes the magic happen, right? That's what allows us to read in the foot pedal signals coming in, do all our checks, write the code, everything's good, send out a digital signal, which is converted to analog, and that goes to the inverter. And that directly controls how much torque the motor is acting with and how fast we go, right? How fast we accelerate. Any questions? So ideally, and everything is sort of defined by the inverter, right? We kind of have to play its game in terms of what it wants as an input, right? If it's expecting a 0 to 5 volt analog input, we kind of have to give it that. Whether it's our foot pedal straight to there, which we can't do because we want to be safe with all these checks, or with our analog signal from the VCU. Some other inverters, especially higher cost ones, and more sophisticated inverters, especially when you get to higher power levels, they're going to have a different method of torque request. So instead of having a 0 to 5 volt signal, considering how important that signal is and how that signal is responsible for moving a 500-pound behemoth vehicle plus your life, instead of the 5 volt signal, they'll take in something called CAN. Right, this is called controller area network. We've mentioned a couple times, it's a super robust signal that's used all the time in the automotive industry. It comes in 2 wires like this. And so this is a digital signal, right? You get to send your signal digitally. So no need for a DAC. Microcontroller sends this. And inside here, we can put a bunch of different messages, different speed requests we would want, different torque requests primarily. If you want to limit the current, if we want data back from the motor, like how fast it's spinning, the current in all of these phases, the phase voltage, it can actually spit that back too. So you can get a lot of really useful information from the inverter over this digital communication. And unfortunately, ours doesn't have this, right? We didn't get to choose the best, most high-performing inverter that gives us all the data because of money mainly. So as a design team, we're strapped for cash all the time. And we were super lucky to get both the inverter and the motor, plus the batteries, all sponsored to us from a company in Vancouver. And so that's like $15,000 to $20,000 that we didn't have to go and knock on doors to get. And so we make do with what we have, right? We use a 0 to 5 volt analog signal, make it as safe as possible, and try to make the reliable car. Obviously, for you guys, when you're making the car after this one, you get to pick, right? You get to pick exactly which inverter you want to use. You get to pick exactly how you want to send a torque request, what information you want to get back, how safe how safely you want to implement your signals, as long as you're in accordance with the rules, right? You could be even safer if you want. But again, that all depends on, can you afford this, right? And this is going to be upwards of 5K. That's usually on the cheap end as well, right? And the only way we can pay for this, the school, it's not the school's job to give teams money, right? So the way we do this is going out and doing sponsorship, and that's what pays for our cars and us racing. So that's the digital to analog converter. Very useful, especially in our case. And you can understand it's sort of just the dual to an analog to digital converter. Same idea, you're converting one to the other. From digital to analog, it's not going to be perfect, but usually you can get closer than you need, for example. Yeah, so we only use this for this one application in the car. We don't have any other digital to analog things that we use. And sometimes if you don't have, like let's say you don't want to pay money for an external DAC, or you don't have one internally, sometimes what you can do is kind of cheat a little bit. So this is probably not doing it justice, but this is something called pulse width modulation. That's just one application of it. It's incredibly powerful and used everywhere. So the idea is that you're just turning on and off your GPIOs really quickly. That's the main idea. So it's all digital, right? You have a digital signal. So let's say you're using a GPIO. There are actual pins dedicated to this. So this acronym is PWM. Right, but the idea is that within a certain period, let's say 1 second, you have your GPIO high for half of it, for example, and then low for another half. And then the cycle starts again. Half, low for half, 2 seconds. Right? Off for half, 3 seconds. So this is a 1 and a 0. So this time here, like this 1 second period where things cycle, that's called the period, obviously. And the amount of time for which your signal is on versus off is called the duty cycle. So calculate it by saying time on divided by total time. Or like period, I think is a better word to use. Does that make sense? So we were on for half a second of the whole 1 second period, 50% duty cycle, right? This is 50%. If we're on for 0.75 seconds and off for 0.25, right, 1 second, and starts again. .75 seconds. So you can imagine, right, 75% duty cycle. Works the same thing the other way too, right? If you're on for only a little bit of time and off for most of the time, this would be 25%. And you get to decide this. As the embedded systems engineer, when you send your signal out, you get to pick the duty cycle and the period of your signal, right? And there's so many different applications for this, especially when it comes to switching semiconductors like MOSFETs. There are a lot of applications where you want to switch them really quickly, on and off, to do different things. Switching mode regulators, switching mode power supplies, which Jared's going to talk about next week, and that Raphael's looking into right now, rely heavily on this, right? And so because of how important it is, people came up with the PWM block, right? So you remember inside our microcontroller, we have a bunch of little peripherals, right? Little building blocks. And we've talked about so far the ADC, right? Talked about the GPIO. Some microcontrollers have the DAC inside. And they literally created a PWM one. So much so that you sometimes, and for the TMS-70, you don't even need to manually do this. You don't need to say, turn on, turn off, turn on, turn off, turn on, turn off, which you normally would. All you need to do is in your setup code, specify these things, right? Specify how quickly you want this to happen, the period, and then specify for how long you want your signal to be on versus off. And just by setting these two things, as soon as you enable that signal in your code, it'll automatically start doing this for you, right? So super useful. Now, this is not analog, right? This has nothing to do with what we were talking about before, especially because it's literally just digital turning on and off really quickly at different duty cycles. But you can kind of convince it to become analog. And basically what that means is that, so let's say my signal was on for half the time, then off for half. What you do is you basically try and filter out those changes. So Jared's already talked about an RC filter, right? So an RC filter is a low pass filter. It doesn't like sharp changes, doesn't like AC, high frequency. And so by sending a PWM signal with the right frequency, let's say something like 1 kilohertz. So what that means is that, remember, frequency is 1 over period. So our period here is 1 millisecond, right? And here to here is 1 millisecond. So that means that this cycle happens 1,000 times a second, right? If we do that and then send it through a filter, we actually kind of get an analog signal out related to what the duty cycle was. So this is, let's say, our logic level was 5 volts, and we're operating at a 50% duty cycle. 5 volts. We kind of get 2.5 volts out, right? And if we did 70%, 75%, through our RC filter, we kind of get so what would it be? 3.75? 75% of 5 volts. And it definitely depends on how you pick these components and what your frequency is here and your period for your PWM signal. But this is definitely a way to get sort of a quick and dirty analog signal if you need one. Not super precise. You can imagine the bigger you make these components, like the capacitor, the more you're going to be able to filter out. So you're going to get a steadier signal. So it's going to be less of this change and ripple from your digital signal, but you're going to react more slowly. So if I want to change it from 75% down to 25%, right? So that would look something like this, right? Like literally the opposite. Oops. On for a little bit, off, on for a little bit, off, on for a little bit, off, because I want to get down to 1.25 volts, right? I want to get down to here. If I have a big capacitor, it's going to make my voltage really steady, but it's going to make my transition really slow. And so there's always a trade-off, right? can have a filter that filters a lot for you, but acts really slowly to changes. You can have a filter that does not filter a lot for you, right? It keeps it kind of noisy, but then it reacts super quick to changes. Right? It's kind of noisy, but then quickly drops, but then still stays noisy. So you kind of have to balance and find a point at which you're willing to accept the amount of noise or the speed. But that's essentially what you would do if you really wanted an analog signal, but you're kind of in the lab and stuck, or you didn't have access to an external DAC, or didn't have the budget for it. That's something you would do. This is actually what we did on our first go-kart for Team Phantom. We didn't have a DAC or anything. We just had the launch pad. So we shoved one of these on the end, and we PWM'd it and got kind of good enough analog signal to control our smaller inverter for our little go-kart. But that is something you can do. Okay, any questions? Mostly conceptual at this point, especially for the filter, but you can play around with different values to work on trade-offs and stuff, right? So in summary for today, we said the digital to analog converter is very similar to the analog to digital converter in the sense that they have some resolution, number of bits, which is how basically how many little chunks can I split up that analog signal into. And there's an analog voltage reference, right? And that decides what's the spread, how high can I send the analog signal that I'm spitting out, and how high can I sample it when it's coming in for the ADC, right? Analog voltage reference. We talked a little bit about what the car does, so foot pedal, right? So Team Phantom's car, wow, I've zoomed out a lot. Team Phantom's car. Why do we have a DAC, right? And the reason was mostly due to our inverter, right? But also that foot pedal is so critical, right? So we send the two signals to the ECU, and that sends them, does the checks, okays them, and then sends it to the inverter, right? So that's our torque path in the car. And then lastly, we mentioned what are some quick and dirty ways you can create it. So PWM, fantastic technique for whatever you need to switch things really quickly. And then you can filter that to get a very quick analog signal. Any questions? We need 3 before we can get out of here. Raphael, any questions?
I got kicked out for the big part of it, so yeah.
Should I start again or from the beginning?
Round 2, let's go.
Yeah. Andre, any questions?
I just asked them the second I was confused. I think I'm good now.
Okay. I'll keep going. I'll call everyone's name if I have to. Elena?
I was kind of confused at the beginning. When you were talking about VREF,
Cool.
and you had like 5 volts, and then you had 3v3. What does 3v3 mean?
Yeah, good question. EV3. equals 3.3 volts.
Okay.
It's just a shorthand. Yeah, it's just shorthand because in the past people would kind of print 3.3 volts on a big
Mhm.
schematic paper, and then you'd sort of squint at it and you'd miss the decimal. So
Mhm.
small. Some people would think it's like 33
Yeah.
volts.
So it could be literally like anything, and just the number after the V would be the decimal.
That's right. So this V
Okay.
kind of acts as
Yeah.
the decimal.
Okay, gotcha.
So it's very
Thank
common.
you.
3v3. Yeah. 1v2. Use that a
Mhm.
lot. What would that be?
1.2.
Yeah.
Cool.
That's right.
Thanks.
Cool. Good question. Thank you. Who's next? Got two more. How about Yash, the embedded legend himself? Please praise us with your questions. Yash, please. Please, I'm begging. Don't do me like this.
You don't have it.
Damn it, Yash. You have no questions. All right. We're going to the big
I'm gonna
guns.
think about
Jared. Okay. Wow, Yash. Thanks for nothing.
Your lesson's
Jared,
just
take
too
us
good,
home.
man. Too comprehensive.
Wow. Okay.
Actually, I got a question.
Yeah.
What do the colors have to do with this?
Oh God. I don't know. Make of it what you will. I should probably make my color arsenal a little better. I always go to this sort of pencil one, but it's like garbage. When I'm zoomed in, it's just blurry. Yeah, so maybe I'll prepare better next time.
All right,
But
thanks for the
nothing
lesson,
really.
man. I'm gonna go eat dinner.
All right, bye. Last question, Jared, go.
Oh wow, I feel so special.
There you go. Last.
Is the question the counting? They counted.
If we are using this to control an inverter,
Yeah.
how fine of steps do we kind of have to achieve? Or yeah, how fine do we have to actually go to be able to get a sinusoidal look?
Good question. So we have a three-phase inverter, right? What that means is that theoretically, your phase voltages should look something like this, right? And the other one would be somewhere here. And then the other one somewhere up here. Right? This is what the inverter's job is to do. So all of this comes under the domain and the job description of the inverter. So it's constantly generating these three-phase waveforms that it's sending to the three phases of the motor. Right? And the motor schematically looks something like this. Right? So these are coils of wire known as a phase. And so probably would I'd color coded this would have been better, but this applies to the voltage across each of these. Right? So the signal that the inverter is taking in is not related to how fine a sine wave voltage we get, right? Like let's say I only had, like my DAC was only like 2 bits. I can only send an analog signal out that was like, ooh, like nothing, right? That doesn't mean that my phase voltages are now super crap, right? That's not what that means. All that means is that the inverter is only going to have 2 levels of torque request, right? So it would only have like 0 and 100, right? If I had 8 bits, like we do, and we have a 5-volt analog voltage reference, right? That means that we theoretically have, so if this were our signal, it's 5, 8 bits, 2 to the 8, 256 steps, right? And so you chomp this up. So we theoretically have 5 volts divided by 256 equals a resolution of 0.0195. 0.195 volts. So we can jump up in little increments of this amount of voltage. But all that means to the inverter is that it's taking a different reference in, right? With whatever reference it takes in, like, oh, I should be at 10% torque or 50% torque or 80% torque, it still has the capability to generate these super smooth waveforms, right? It's just going to do them at different amplitudes and different frequencies based on however much torque we want, right? So if I wanted more torque, I would need more current, and so my current waveforms would be of higher magnitude, regardless of whatever my input voltage was. If I had a high degree of resolution or low degree of resolution, all the inverter cares about is the absolute value at that point. When it's given that, it can now go and do its math and do its conversion into the 3 phases, right? And it's going to have its own internal resolution to actually generate these properly, right? Independent of whatever you're shoving into the input signal. It has its own resolution and its own way of generating those waveforms. Does that make sense?
Yeah.
Cool. All right, lesson adjourned. Next week we have a example circuit of how a DAC works with some other things, another useful application of it. And it's actually a different interview question that I once had where they kind of plop this down in front of me and they're like, all right, tell us how it works. So we can test you guys all next week. All right, bye.